Hello students, welcome to the class of Advanced Strength of Materials. Today we are going to study bending and shear stresses. Now we are very much familiar with this two term, bending and shear stresses, as we have done lot of bending and shear force diagram in the previous classes. Today we are following the syllabus prescribed by West Bengal State Council of Technical Education and Vocational Training, and today's course objective is to understand the theory of simple bending, calculate bending stress in beam cross section, demonstrate an ability to determine shear stresses in beam of various cross section. Now we all know that bending is usually associated with shear. Any structural member or structural member like beams are subjected to external forces that give rise to bending stress as well as shear stress within them. Now for simplicity we neglect the effect of shear, okay, and consider moment alone to find the stress due to bending. Now this particular thing that we can see here in this simulation is that this cantilever beam is being acted upon by some external force, where the uppermost layer is in tension and the lowermost layer is in compression. These two unbalanced forces will give rise to shear force within this beam. So the theory that deals with the finding stresses due to pure moment at a section is called simple bending theory. Now here in simple bending theory we will not consider shear effects, okay, so effect of shear force is negligible in these cases. Now this theory is also backed up with a lot of assumptions here, and there are 6 assumptions mainly. The first assumption is the beam is initially taken to be straight and every layer of it is free to expand or contract. The next one, the material is taken to be homogeneous and isotropic. Third point, Young's modulus is same in tension and compression. Fourth point, stresses are within elastic limit. Fifth point, plane section remains plane even after bending. Sixth point, the radius of curvature is large compared to the depth of the beam. Now this last 2 point, plane section remains plane even after bending, this point is very much important, and the last point, the radius of curvature is large compared to the depth of the beam cross section, is also very important. And the plane section remains plane means the cross sectional area before and after bending of the beam remains same. The radius of curvature, that is the radius with which the beam is getting bent, is much larger than the depth of the beam. And there is a line or a layer passing through the center of the beam which is known as neutral axis. Remember, in the neutral axis there will be no effect of forces, that is no compression, no tension, no deformation, okay. Neutral axis is technically free from all deformations, all forces, okay. Now from this assumption we have to make a relation between bending stress and radius of curvature. Now in the next part here, in this particular part, see, we are having a beam here which is like this one, and this one, my cursor is showing you this beam, okay. This beam, we are taking a section A, B, C, D, where EF is the neutral axis, GH is the elemental layer taken on about which, with which we are going to discuss that how the bending stress and the radius of curvature is linked with each other. Now this neutral axis before and after bending will remain same, that is EF will equal to E dashed F dashed. This GH however differs and it will become G dashed H dashed, okay. Distance between EF and GH is Y, it is shown here, okay. Then the radius of curvature is R, and the arc length will be R phi, okay, that is shown here, this one, okay. Strain in the layer GH, the strain that is being developed in this layer will be Y by R, this one, okay. So in initial days of strength of material we have learned that sigma equals to E into epsilon. So strain we have found out here, this is the strain, okay. And if we take the bending stress as F, then F by E is also strain, stress by E is also epsilon. So F by E is equals to Y by R, that will give rise to F is equals to E Y by R. Okay, this particular equation is the relation between bending stress and radius of curvature. Now we must understand first the position of neutral axis, because we have told that neutral axis is at the center, do not interact with any force, or do not changes under the application of forces. So we must first understand that neutral axis is actually at the center or not. So we have taken an elemental area dA, and the force that is being taken here, application of force that is being taken here is creating a stress that is small f. So the total elemental force, not elemental force, it is force on the elemental area is FdA. Now total force on the cross section of the beam is summation of FdA that we are having here. Okay, but from the equation F is equals to Ey by R, and this is the previous derivation that we have done, so we can substitute the value of F here in this equation, will give rise to E by R summation of YdA. Now this YdA is very much familiar to us, because this is the first moment of area. Okay, so this is the first moment of area about the neutral axis, okay, for a particular cross section. So if we rewrite the equation like this, summation of YdA by A is equals to 0, this is the distance of the centroid from the neutral axis, and this actually shows that the neutral axis coincides with the centroidal axis of the cross section. So this proves that the neutral axis is at the center, is present at the center of the beam, right? Now in the next part we have to derive an equation which is the relation between moment and radius of curvature. Now initially we'll take the stress equation, F is equals to E Y by R, and similarly in the as in the previous derivation we have taken the elemental area dA, and the distance of dA is y from the neutral axis. Force on the elemental area is FdA, and the after substitution the force becomes EY by R, and this is generating a resisting moment about the neutral axis, which will give rise to the equation of EY square by R dA. Okay, so the resistive moment, or the moment of resistance of the cross sectional area, is m dashed E by R summation y square dA. Okay, now this y square dA is very much familiar to us because we know moment of inertia. Okay, from the definition this is the second moment of area about the centroidal axis. Now it is denoted by I. So this particular equation will give rise, or we can rewrite to this particular equation to form a compact equation like m dash is equals to EI by R, right? So since this material or this particular beam is in equilibrium, and so we can say that the resistive moment and the applied moment is same. Okay, and taking that thing into account, we will put like capital M equals to m dash equals to EI by R, or m by I equals to E by R. Now we all know that E by R is equals to F by Y from this particular equation of stress, bending stress. So the equation will give rise to a bending equation. So this particular equation will be substituted here and will give rise to a bending equation known as m by I equals to F by Y equals to E by R. This is the bending equation which is universally important and very much used to design beam structures. Now this particular derivation thus gives the relation of bending moment and radius of curvature, and also gives a relation of bending stress and radius of curvature. Now one thing we have to keep in mind is that what is M, what is I. And the M is the bending moment, I is the moment of area about the centroidal axis, F is the bending stress, Y is the distance of the fiber from the neutral axis, E is the Young's modulus, R is the radius of curvature. Now up to this we have found out all the relations. Now we have to understand how a section or cross section or any beam can carry moment, or the carrying capacity, moment carrying capacity of any section. Okay, from the bending equation, m by I equals to f by y, f is equals to m by I into y. So this is the equation that we have derived in the earlier stages. Now this shows that the bending stress is maximum on the extreme fiber where y is maximum. So any design, while we are going to make any design, this particular stress must not exceed the maximum permissible stress. Okay, so that means if permissible will be the highest limit of any particular section, and that if permissible will always be greater than F max for any particular section, and F max is the maximum load that can be applied on any particular section. So F max will be m by I into y max, which is less than F permissible, and if m is taken as maximum moment carrying capacity of the section, then m y max by I equals to F permissible. So the equation can be rewritten as m is equals to I by y F permissible, and that I by y thus becomes a property. Okay, and this is the property of cross sectional area and is termed as sectional modulus and is denoted by the letter Z. Then m is equals to F permissible into Z, right? So this particular equation give rise to the moment carrying capacity of a section, where we'll find the that how much moment a section can carry. Okay, and F and Z to be precise, Z is having an unit of millimeter to the power cube. Okay, where I is having a unit of millimeter to the power 4. I is the moment of inertia. Now a few examples I would like to share with you all is how to find the value of Z for common structures like solid rectangular structure or a hollow rectangular structure. In case of solid rectangular structure, we will find that I is equals to 1 by 12 BD cube, or y max is equals to d by 2, where Z is equals to I by y max BD cube by 12 divided by d by 2, and that will give rise to Z equals to 1 by 6 BD square. And the hollow structure, likewise here in this solid structure, we will find that hollow structure, the value of I equals to 1 by 12 BD cube minus BD cube, small BD cube, and y equals to capital D by 2, and Z will give rise to I by y max, and that will give rise to 1 by 6 BD cube minus small BD cube divided by D. Now these are the two examples for the value of Z. Sorry, and these are two examples. These are the two examples how to deduce the value of Z. Now in case of this particular portion is completed. Actually this last portion of bending stress, this is the last portion that is giving the conclusion of bending stress. Now in case of shear stress, as we have deduced earlier that F is equals to my by I, we are going to use that particular equation of bending to deduce the shear stress here. Now the force on the element here in the left hand side equals to m by y b dy. Okay, now m by y b dy, where from we are getting this b dy, where from we are getting this b dy, this b and this dy, okay, is the depth. Okay, this one, this depth and this b. Okay, so m by I y b dy is the force on the elemental area or the elemental layer on the left hand side. Now similarly the force on the right hand side will be m plus dm, because there will be a change in moment here to keep that thing in equilibrium, as we all know that this particular section, although it is elemental, but do have some mass. So this will give rise to a moment which is greater than the initially applied moment m. So this moment m plus dm by I y b dy will give rise to unbalanced situation, right? This is much more greater than this one, and this unbalanced force is given by dm by I y b dy. Okay, and if we integrate this particular equation, this particular equation, if we integrate, we will find the intensity of shear, right? So so let us take this equation as integration dm by I y to y dashed and y b dy, and the horizontal force, that is the unbalanced horizontal force, is practically resisted by the shear stress in the horizontal direction, and the intensity of the shear is taken to be as q. And if we try to understand how this is happening, then let's see again, q into this q multiplied by b. Okay, see, this q multiplied by b into dx. Okay, q multiplied by b into dx. Okay, this is the entire intensity. Okay, entire intensity, I mean q is the intensity, and this is the entire block on which the intensity is maximum, and this particular entire force, this intensity into the area, will give rise to a force which is equivalent to this one, this unbalanced force. Okay, and this give rise to q equals to m dm by dx 1 by bi integration y to y dashed ya. This ya is again, this ya is basically moment of area. Okay, and now why this a is coming, b dy, we know that b into dy. Okay, this one, this thickness, that is the area. Okay, so the term, okay, ya y to y dashed can be taken as the moment of area that I have just told right now, and which is about the centroidal axis. Now dm by x is equals to f. Okay, dm by x, we have found out that from the initial equations we know that it is f, the force applied. So q is the intensity equals to f divided by bi a y bar. Now from this particular equation we can understand that the extrememost fiber, the extreme shear stress on the extrememost fiber is having shear stress which is 0. Okay, so this concludes the shear stress here, and I would like to show you an example of shear stress for a section, for a very similar section like we have done in the bending stress. Here this is a square section, and in the square section we will find that we do have a neutral axis, and the depth of the square is d, and is taken to be as d by 2 above the neutral axis, and again d by 2 below the neutral axis, and the b is the base, and y is the distance of the elemental area that we have taken here. This elemental area that we have taken here, this having a center, let's say c dashed, and the distance between this center of this elemental area to this neutral axis is y. So we are going to apply the equation q equals to f by b bi. Okay, so that will give rise to that will give rise to the stress intensity within that particular block. So the a that will be derived as a equals to b into d by 2 minus y, and y bar is the maximum distance, so y equals to, y bar equals to y plus 1 by 2 d by 2 minus y plus 1 by 2 multiplied by d by 2 minus y equals to 1 by 2 d by 2 plus of y. Now since it is a rectangular cross sectional area, so I equals to 1 by 12 bd cube, it is known to all, moment of inertia. Now from the equation we have derived earlier that q is equals to f by bi equals to ay bar, where we have to substitute the values. Okay, and so we are substituting the values here, and we are getting that 6f b d cube d square by 2 minus y square. One thing, q is equals to f by bi, q equals to f by bi multiplied by ay bar. So we have to substitute value of a, value of y bar, and value of I here in this equation, right? So this will give rise to 6f bd cube d square by 2 minus y square. Now this particular equation is parabolic in nature, we can see from the equation itself. So at d by 2, at y equals to d by 2, now this particular thing is known as the boundary condition. Okay, this particular thing is actually known as boundary condition, and where where we are going to put the value of y equals to d by 2, and it will give rise to that q equals to 0. Then this give rise again to the initial statement that we have written here, that shearing stress at the extreme fiber is 0. So this particular boundary condition gave rise to that particular thing. Okay, so at y equals to 0, that means at this particular point, okay, the q is maximum. That means the shear stress is maximum at the y equals to 0 position. So average stress intensity is the shearing force divided by the area. Thus maximum shear stress is 1.5 times the average shear stress that we can find here from this particular equation in this particular block. Okay, and see this one, the maximum shear stress is 1.5 times the average shear stress that we have derived here in this particular block. So this concludes the shear stress, and we do have many other sections here. I have just discussed only the rectangular section. Please go through this entire video and try to find out your queries. I know you will find a lot of queries here, because this particular chapter is tricky, precise, and many things are there, many things are happening inside. So please go through the video very carefully, and please do comment on the video, and I know you will have a lot of questions. Please inform me if you have having any question, or you can comment a question so that I can get to you and get up to you, and I can answer that question and can solve your query. And be very attentive while listening to this video, because this video is practically a bit tricky. Okay, it's this particular chapter is a bit tricky than any other chapters. So thank you for your attention. Thank you once again.